F8U-1 Crusader, the Navy's first fighter capable of sustained operation at supersonic speed. It is powered with a J-57 T-4A thrust of 10,200 pounds. The engine includes an integral afterburner and, with afterburner, has a maximum thrust of 16,000 pounds. The aircraft has been so successful in fleet operations and has demonstrated such a good growth potential that most available aircraft have been retrofitted with the latest F8U-1 modifications. Differences in the F8U-1E, 1P, 2, and 2N aircraft are covered in later films in this series. The Crusader has an approximate gross weight of 27,000 pounds. It is just over 55 feet long. The span is slightly under 36 feet. With the wings folded, the span is 22.5 feet. The maximum height is just under 16 feet, with wings either folded or unfolded. The F8U-1 is capable of carrying two Sidewinder 1 or 1A missiles and uses an Arrow 10L1 armament control system. 4 fixed 20-millimeter guns are mounted low in the forward fuselage. Normal load is 125 rounds per gun. This film, in 2 parts, shows the Crusader's primary aircraft systems and their supporting features. In this part, we shall see the fuel, lubrication, electrical, and the cabin air conditioning and pressurization systems. Let's first look at the fuel system in the airframe. The main system fuel is stored in one main fuselage and 2 mid-fuselage bladder-type cells, which are interconnected with the main cell. Transfer system fuel is stored in 4 interconnected aft fuselage transfer cells, which are also bladder type and in a wet wing tank. The only way to fill the tanks on the ground is by pressure fueling. External electrical power must be used during refueling procedures. For refueling operations, the master generator switch must be in the external position, and all other switches must be off. This will allow the external power source to provide AC and DC power for the operation of fuel system gauges and shutoff valves. The wing may be either in the up or down position. If the fuel selector is set at partial, the transfer system will be filled, but only 432 gallons will go into the main cells. With the selector in forward cell position only, the main cell will be filled. In-flight refueling through a retractable probe permits refueling of the entire airplane to increase its operational range or on-station time. The main cell holds 432 gallons, and the 2 mid-fuselage cells hold 44 gallons each, for a total of 520 gallons in the main system. Using JP5, the total is about 3,530 pounds. The 4 aft transfer cells hold a total of 174 gallons, and the wing tank holds 579 gallons, for a total of 753 gallons in the transfer system. Using JP5, the total is about 5,100 pounds. Total fuel aboard adds up to 1,273 gallons, or about 8,650 pounds. The wing tank and fuselage cells are pressurized by air from the airplane pressurization system. A combined pressure regulator and relief valve maintains pressure in the wing tank when the fuel transfer switch is in either the on or the pump off position. Should the combination regulator and relief valve fail, another relief valve limits the wing tank pressure. Excess pressure escapes through the vent line in the right wing. To dump the fuel from the wing tank, the fuel dump switch is placed in the dump position. This increases the wing tank airflow and opens 2 dump valves, 1 in each wing tank. Normal dumping requires about 5 minutes. The rate of dumping will increase with nose-up attitudes and at power settings over 80% RPM. If the wing tank is not pressurized, dumping requires approximately 15 minutes. Another pressure regulator maintains pressure in the fuselage cells at all times. In case of regulator failure, a relief valve in the vent system limits cell pressurization. Excess pressure in the cells is relieved through the overboard vent, located aft on the left side of the fuselage. If the normal cell pressurization fails, an emergency ram air scoop located high on the right side of the fuselage will provide partial pressure to the fuel cells. Here is how the fuel transfer system works. Fuel from the pressurized wing tank flows through the fueling and transfer manifold to the main cell. With the fuel transfer switch in the on position, a transfer pump located in the left aft transfer cell simultaneously delivers fuel from the cluster of aft transfer cells to the main cell. Float valves in the main cell allow the transfer fuel to flow into the main cell when its quantity is below approximately 2,800 pounds. The aft fuel transfer pump stops operating whenever the airplane is in inverted flight or in a dive in excess of 15 degrees. The ratio of fuel flow between the wing tank and transfer cells is slightly more than 1:1. When the transfer cells are empty, the fuel transfer pump light will glow. The light will also glow if the pump fails. In this case, there is no other way to transfer or dump aft transfer fuel, and a landing should be made before the main fuel level reaches 1,200 pounds due to CG considerations. Placing the transfer switch to the pump off position will turn off the transfer pump. The wing tank will continue to be pressurized to allow the remainder of the fuel to be transferred if the cabin pressurization switch is in the cabin pressure position. If this switch is moved to the cabin dump position, wing tank pressure is cut off. When the wing tank is empty, the transfer switch should be left in the pump off position to keep the wing tank pressurized until it is time to land. In case of pressurization system failure in aircraft with wing ram air scoops, fuel from the wing tank will continue to flow at a slightly reduced rate. Fuel from the mid-fuselage cells will gravity feed into the main cell. Whenever the amount of fuel in the main cell drops to approximately 150 gallons, or 1,000 pounds, the low-level warning light on the instrument panel will glow. Now, here's how the fuel is fed from the main cell to the engine. Placing the engine master switch in the on position energizes 3 fuel boost pumps on the bottom of the main cell. It also opens the engine fuel shutoff valve in the fuel line to the engine. A dive of 15 degrees or more, climbs greater than 120 degrees, and rolls greater than 90 degrees will automatically energize 2 inverted fuel boost pumps. 2 boost pumps will supply sufficient fuel to the engine for any flight condition. In case of electrical failure, 1 boost pump will be powered by the emergency air-driven generator when its switch is in the on position. In the land position, all pumps are cut out. So much for the airframe fuel system. This is what happens in the J-57 engine fuel system. The fuel is pumped through the shutoff valve to the 3-stage engine-driven pump. The centrifugal pump in the booster stage boosts the fuel to higher pressures. The fuel continues through the engine stage pump, through the transfer valve, and on to the fuel control unit. Should the engine stage pump fail, the transfer valve will automatically allow fuel from the afterburner stage pump to flow to the fuel control unit. The fuel pump warning light will glow to indicate that the engine stage pump has failed. In this case, the afterburner should not be used. Back to normal again, we see that the fuel passes through a hydromechanical fuel control that automatically meters the fuel flow according to the throttle position and ambient conditions. If the fuel control fails, the fuel control switch should be placed in the manual position. If circumstances permit, the throttle should be in idle when switching to manual. Fuel flow to the engine now bypasses the automatic fuel metering functions of the fuel control and is manually controlled by throttle movement. Caution must be exercised in moving the throttle to prevent excessive exhaust gas temperature or possible flameout. From the fuel control, the fuel passes through a fuel oil heat exchanger where the fuel absorbs some of the oil's heat. The fuel then continues to the fuel nozzles in the engine. Returning to the afterburner fuel system, we see that with the throttle in the maximum detent, the fuel leaves the afterburner stage pump and continues to the afterburner fuel control unit and on to the afterburner fuel nozzles. The afterburner output is proportional to the degree of throttle modulation. This completes the discussion on the fuel system. Let's cover briefly the lubrication system of the J57 engine. This engine has a self-contained lubrication system. The oil is stored in a 5 1/2 gallon capacity tank. A high-pressure pump forces oil to the main bearings and accessory drives of the engine. 6 scavenger pumps return the oil to the tank through an air oil cooler and a fuel oil heat exchanger. Normal operating pressure is 45 plus or minus 8 psi. Let's go on to the F8U electrical system. AC and DC generators mounted on the same shaft and driven by an air turbine power the electrical system. The air turbine is driven by bleed air from the engine compressor section. The AC generator has an output of 115 and 200 volts at 400 cycles and is rated at 9 kVA. It supplies power to the primary, secondary, and emergency AC buses. The 50-ampere DC generator supplies 28 volts DC power to the primary, secondary, and emergency DC buses. This electrical system is without a battery. If the Crusader's electrical circuits need to be energized on the ground and the engine is not running, external AC-DC power must be used. After external power is plugged in, the master generator switch must be placed to external to energize the electrical system. In normal operation, when the master generator switch is on, the AC-DC generators supply power to the whole system. If the AC generator fails, the DC power will still be available. However, when the DC generator fails, AC power is no longer available. The airplane is completely without electrical power until the emergency generator is in operation. To put it in operation, the emergency generator switch should be checked in the off position. Then the emergency power handle on the forward left console is pulled aft. This will allow air pressure from an air bottle to extend the emergency power package from the right side of the fuselage. The ram air turbine will then drive the emergency AC and DC generators and the emergency hydraulic pump. Placing the emergency generator switch to on after the air turbine has attained operating speed will allow the emergency AC-DC generators to energize the primary and emergency AC-DC buses. A light next to the switch will glow, indicating that power is being supplied. However, at lower air speeds, a reduced current is generated. For adequate power, at least 175 knots must be maintained with the switch in the on position and 145 knots in the land position. The emergency are energized. These control for the circuits powered by the primary and secondary AC and DC buses. Now that the electrical system has been conditioning and pressurization system in the Crusader. Basically, it's similar to the system used in most systems. Bleed air under pressure from the engine compressor section and ram air from the engine intake duct are directed through the air conditioning unit. Within the air conditioning unit, the temperature of the bleed air from the engine compressor section is reduced as it passes through the coils of the heat exchanger. Some of the warm air that has passed through the heat exchanger coils is cooled further by expanding refrigeration unit to supply the cool air. To supply warm air, bleed air from the engine is used directly. Thus, the pressurized air passing through the air conditioning unit is conditioned to furnish the heating, cooling, ventilation, and pressurizing requirements of the airplane. 3 integral control valves in this system provide automatic air pressure regulation. The cabin air pressure regulator valve provides automatically regulated pressurization above 8,000 feet. Below this altitude, the cabin is unpressurized. Moving the switch on the air conditioning panel to cabin pressure will provide cooling air to the nose cone armament system, pressurize the wing cells, and automatically build up cabin pressure. The indicator on the right console shows the cabin pressure altitude. A cabin dump valve automatically relieves excess positive and negative cabin pressure differentials if the cabin air pressure regulator valve fails. The manifold pressure regulator valve automatically controls pressure and airflow to the cabin and maintains proper balance of pressure cabin and full pressure suit. When cabin pressure is dumped, this valve closes and stops the airflow to the cabin. Positive airflow to the pressure suit and to the integrated continues. A temperature control on the air conditioning panel makes it possible to automatically control inlet temperature into the cabin and full pressure suit. The controller knob can be turned to select any desired temperature. The setting of the controller knob regulates the operation of the temperature control bypass valve to automatically provide the cabin temperature that is selected. Placing the defog switch in on directs hot air through manifolds over the windshield and side panels to eliminate condensation. The tendency toward fogging may be prevented during high-altitude loiter by the continuous use of the defogging system above 30,000 feet. Also, on fast descents, to prevent fogging, maintain a defogger turned off and the emergency vent air knob rotated to open the air inlet. In this film, you have seen the fuel, lubrication, electrical, and cabin air conditioning and pressurization systems of the F8U-1. Part 2 shows the operation remaining systems. This film, Part 2, covers the following F8U-1 Crusader primary aircraft systems and their supporting features: utility hydraulic, pneumatic, power control, and flight stabilization systems. Let's start with the utility hydraulic system. A reservoir supplies fluid to a variable volume engine-driven pump that develops 3,000 psi pressure. It operates the following components: the 2-position wing, leading edge droop, landing gear, wheel brakes, nose gear steering, a resting gear hook, speed brake, wing fold, in-flight refueling probe, and the rocket pack, which is not used unless operationally necessary. Note that the utility hydraulic system provides pressure to activate all the hydraulic components except the control surfaces. A hydraulic gauge mounted on the instrument panel shows system pressure if the gauge selector switch is in the utility position. The hydraulic system's warning light will glow when system pressure falls below 700 psi pressure. Let's look at the controls for the system. To raise the wing, first, the downlock handle is pulled aft. Then the wing incident handle can be moved aft. The release switch must be depressed and held throughout the movement of the wing incident handle. The leading edges will extend to the landing droop position of 25 degrees, regardless of cruise droop switch position, and the wing will rise 8 degrees. In addition, the wing flaps and ailerons will extend mechanically 20 degrees. The landing position of the wing permits relatively low takeoff and landing speeds with increased visibility. To lower the wing to clean condition, depress the release switch and push the wing incident handle forward. Be sure to hold the release switch down during any movement of the handle. After the wing is down, the locking handle is brought forward to lock the wing incident's actuating cylinder and handle in place. The throttle grip is used as a cruise droop switch. Rotating the throttle grip forward will move the leading edges to a cruise droop position of 6.8 degrees down. The arresting gear hook is retracted and held in place by utility hydraulic pressure and a mechanical latch. It is mechanically released and extended by pressure from its own accumulator. A warning light in the arresting gear handle on the right console will glow when the handle and hook positions do not agree. The speed brake operation is conventional. A 3-position toggle switch on the throttle controls the operation of the speed brake. Note, however, that the brake in the full down position extends below the landing gear. The speed brake, therefore, is automatically retracted when the wing is raised. In an emergency, an override circuit permits extension of the speed brake with the wing up. Landing gear extension and retraction is standard, with indicators on the instrument panel. A light in the handle will glow when the landing gear is out of phase with the handle. The landing gear emergency downlock release switch will permit the gear retraction handle to be placed to the wheels up position with the airplane on the ground if necessary. Never use this switch to retract the gear for normal operation. On later F8Us, a wing position warning light on the instrument panel will flash when the gear and wing are not in correct relation to one another or when the wing is unlocked in the clean configuration. To facilitate taxiing, the nose gear can be steered with the rudder pedals if the nose gear steering switch on the stick is held depressed. Self-adjusting wheel brakes are power boosted by the utility hydraulic system. An accumulator provides hydraulic pressure for from 6 to 12 boosted brake applications. This provides an ample number of power applications for most ground handling operations. If the accumulator pressure is depleted and the engine is not operating, manual brake application without boost is still possible. In manual braking, very heavy foot pressure is required to apply the brakes. The wing fold operation is standard. Utility hydraulic pressure actuates the wings and the hinge lock pins. To spread the wings, depress the wing fold lever. Then, after the wings are spread, wait several seconds and stow the mechanical wing fold lock lever, which safeties the lock pins in place. Red warning flags on both sides of each wing provide a double check that the wing lock pins are properly positioned. A retractable in-flight refueling probe in the left side of the fuselage is extended and retracted by utility hydraulic pressure. Placing the in-flight refueling probe switch in the out position will depressurize the wing tank, de-energize the transfer system, position the fuel valves to accept fuel, open the probe fairing door, and extend the probe. The in-flight refueling probe light on the instrument panel will glow when the fairing doors open. Placing the probe switch in off, regardless of probe position, returns the transfer system to normal operation. Holding the probe switch in the in position will re-energize the transfer fuel system and reposition the fuel valves for normal operation, retract the probe, and close the fairing door. The probe light will go off when the fairing door is completely closed. Releasing the switch to off will de-energize the door selector valve. Now that we've covered the utility hydraulic system, let's look at the pneumatic system, which provides air pressure to operate certain components if the utility hydraulic system fails. The air supply is contained in 3 high-pressure air bottles, a 50, 375, and a 900 cubic inch bottle, one for each of 3 air circuits. System pressures are read, and the circuits are serviced on the left forward fuselage. There are no gauges in the cockpit to indicate the pneumatic system pressures. The 375 cubic inch air bottle provides pressure to extend the wing leading edge to the landing droop position. Pressure from the 50 cubic inch air bottle raises the 2-position wing. The 900 cubic inch air bottle provides pressure to extend the leading edge of the wing to cruise droop, to lower the landing gear, and to apply the wheel brakes. Pressure from the 900 cubic inch bottle is used to extend the power package from the right fuselage when there is need for emergency electrical or hydraulic control power. Pressure in this circuit also is used to arm the guns and to open and close the gun vent doors. In the event of a utility hydraulic system failure, pull the downlock handle aft to the wing unlocked position. Then raise the guard and push the wing incident handle forward to the over travel position while holding the release switch depressed. The leading edge will extend to the landing droop position. Continue to move the wing incident handle inboard and then aft in the wing emergency up slot while holding the release switch depressed. The wing will now raise to the landing condition. Emergency operation of the landing gear is accomplished by lowering the gear handle to the down position and pushing it forward, then turning it clockwise and pulling aft. Air from the large bottle will extend and lock the nose gear and unlock the main gear doors. The main gear falls by its own weight and is blown back to a locked position. Emergency brake operation is performed with the handle located outboard of the throttle. Moving the handle aft directs pneumatic pressure to apply both wheel brakes simultaneously. The amount of travel of the handle aft will determine the amount of air pressure delivered to the brake lines. Allowing the handle to return forward releases the brakes. However, whenever pneumatic pressure is used, the hydraulic brake system must be bled again before flight. This concludes the section on the utility hydraulic and pneumatic systems. Next, the power control systems. 2 independent hydraulic systems, Power Control Systems 1 and 2, provide power to actuate the Crusader's control surfaces. Each system has its own reservoir and is powered by its own variable volume engine-driven pump, developing 3,000 psi. PC1 supplies hydraulic pressure to one side of the tandem cylinder in each power package, and PC2 supplies hydraulic pressure to the other side. Roll stabilization corrections are applied through the PC1 system. Yaw stabilization and the spoilers operate off the PC2 system. System pressure is read off the hydraulic pressure gauge located on the lower right of the instrument panel. A 3-position toggle switch next to the gauge selects the system to be checked. When either power control system pressure drops below 1,500 psi, the hydraulic system's warning light will glow. Below 450 psi in the PC2 system, yaw stabilization and operation of aileron spoilers is lost. PC1 still provides pressure to the control packages. If, in addition, PC1 should fail, the airplane control system will be without hydraulic power. When the emergency power package is extended into the airstream, hydraulic pressure is restored to the PC1 system. The power package is driven by an air turbine which powers the emergency generators and hydraulic pump. The pump will supply 2150 psi pressure to the PC1 system lines. PC2 remains inoperative. Hydraulic pressure produced by the emergency pump will be indicated on the hydraulic pressure gauge if the check switch is in the PC1 position. Now let's continue with the description and operation of the F8U flight control system. This system is a true power control system, since the work of moving all the control surfaces is done by hydraulic power cylinders. A power control package is provided for each aileron, one for the rudder and one for each unit horizontal tail. There is also a power cylinder to move each spoiler. Each control package consists of a tandem actuating cylinder and slider valves, which regulate the flow of hydraulic pressure to the proper side of the actuating cylinders. The stick and rudder pedals are mechanically linked to the slider valves. Thus, moving the stick or rudder pedals moves a slider valve within each control package, which allows hydraulic pressure to move the actuating cylinder. Through mechanical linkage, the cylinder in turn moves the control surface. Whenever the aileron is deflected more than 2 degrees above the clean condition neutral position, mechanical linkage moves the slider valve to allow hydraulic pressure to actuate the spoiler control surface. A spoiler forward of each aileron increases the rate of roll at low altitudes and high speeds. The spoilers are slaved directly to the aileron controls and function in both the clean and landing conditions. Each spoiler surface comes up in proportion to the amount of aileron travel. The total spoiler deflection is 49 degrees. Because the control surfaces are moved by hydraulic power, the pilot does not feel the aerodynamic forces acting on the control surfaces. He therefore has control fields simulated for him by double-action springs installed in the linkages between the cockpit controls and the power packages. The springs return the control stick and rudder pedals to neutral when released. In the longitudinal control system, there are bob weights to simulate the feel of G-forces and viscous dampers to dampen longitudinal stick displacement. The following flight control system changes occur automatically when the wing is raised to the landing condition. A system of mechanical levers droops the ailerons 20 degrees and changes the aileron downward throw from 15 to 35 degrees from landing condition neutral. The upward throw is increased from 15 to 35 degrees from landing condition neutral. The rudder pedal force is decreased by 1/2, and rudder throw is almost tripled from 6 to 17 degrees. Lastly, the unit horizontal tail is moved to give 5 degrees nose-down trim. To supplement the flight control system, the F8U has an electro-hydraulic trim and stabilization system for trimming and for automatic flight control corrections, which are commonly referred to as damping. The system provides trim and damping about the yaw and roll axes and trim only about the pitch axis. Let's take the rudder first and go over yaw trim and damping. An electro-hydraulic actuator hydraulically extends and retracts the linkage to the slider valve on the rudder power package upon receiving electrical signals from the stabilization amplifier. Trim signals to the amplifier come from the rudder trim potentiometer on the left console. Damping signals originate in the yaw accelerometers. In the clean condition, these signals first go to the gain changer, which regulates the signals in proportion to altitude changes. The signal from the gain changer then goes to the amplifier, and from there to the yaw actuator. Also, during roll maneuvers in the clean condition, an aileron position potentiometer and a horizontal tail position potentiometer send signals to the amplifier to modify the final signal to the rudder. This prevents excessive favorable yaw. In the landing condition, the yaw accelerometer sends its signal directly to the amplifier and from there to the yaw actuator without any other modification. The trim and damping changes are not felt at the rudder pedals. In case of failure of any part of the system, the entire system, including rudder trim, will cut out immediately. The rudder returns to neutral, and the yaw stab warning light will glow on the left console. The yaw stab switch should be placed to off and reset, and then to on. If the light continues to glow, the switch should be placed to off and reset, and left there. The airplane can be controlled safely without yaw stabilization and rudder trim up to 675 knots indicated airspeed or 1.4 indicated Mach number, whichever is lower. Going on to roll trim and damping, we find that it is similar to the yaw system. The electro-hydraulic actuator is located in the linkage to the aileron power packages. It extends or retracts the linkage hydraulically upon receiving electrical signals from the stabilization amplifier. Trim signals from the roll trim potentiometer on the stick send trim signals to the amplifier. In both the clean and landing condition, damping signals originate in the roll rate gyros and are modified by the roll. The signal from the amplifier then goes to the actuator. At low speeds, the pilot does not want large automatic roll corrections during a recovery maneuver. Therefore, the system operates so that the further the pilot moves the stick away from neutral, the less damping he gets. The trim and damping changes are not felt at the stick. As in the yaw stabilization system, in case of failure of any part of the roll stabilization system, the entire system, including roll trim, will cut out immediately. The ailerons will return to neutral, and the roll stab warning light will glow on the left console. The roll stab switch should be placed to off and reset, and then to on. If the light continues to glow, the switch should be placed to off and reset, and left there. In the landing configuration at speeds under 180 knots, the airplane is controllable without roll or yaw stabilization. Remember, in case of a main generator failure, both stabs go off the line and must be reset after the emergency power package is operating. Pitch stabilization is not provided in the Crusader. Elevator pitch trim is accomplished by an electric motor actuator which is located in the linkage to the unit horizontal tail power packages. The actuator extends and retracts the slider valve on the power packages upon signals from the pitch trim amplifier. Signals to the amplifier originate at the pitch trim potentiometer on the stick. The wing incidence potentiometer has one function. When the wing is raised, it signals for a 5-degree nose-down trim change. As in the case of roll, pitch trim changes are not felt at the stick. In case of failure of the stick pitch trim potentiometer or of the wing incidence potentiometer, the emergency pitch trim T-handle on the left console must be pulled up. The T-handle can then be used to control the electromechanical actuator for pitch trim. This completes the discussion of the flight stabilization system. This film, in 2 parts, has described the operation and supporting features of these primary F8U systems: fuel, lubrication, electrical, cabin air conditioning and pressurization, utility hydraulic, pneumatic, power control, and flight stabilization. Further study of your flight handbook and discussion with experienced F8U pilots will help you become a better qualified Crusader pilot. This film shows shows the inspections, checks, and operating procedures for the F-8 on the ground. The procedures recommended in this film are generally applicable to all series F-8U aircraft, but specifically pertain to the F-8U-1 airplane. Additional training films in this series cover the variations in other Crusader. Consult the latest flight handbook and technical bulletins for your particular aircraft, model, and bureau number. After you have briefed, determined the proper takeoff minimum pressure ratio, and filed your flight plan, you are ready to proceed to the line. The pre-flight inspection is standard, consisting of a visual inspection of the general condition of the airplane. This includes making sure the protective covers have been removed, vents and ports are unobstructed, access doors and panels are secured, and that there are no hydraulic or fuel leaks. Here are some special items to check. Nose cone secured. Intake duct for obstructions. In the nose wheel well, check the approach lights for damage. Check the strut extension, tire condition and inflation, and the hydraulic components for leaks and general condition. Moving aft on the fuselage, check the utility hydraulic reservoir for proper servicing. In the right wheel well, check the right landing gear strut for extension and leaks. Check the tire inflation and condition. Also, brake discs for condition and wheel well for general evidence of leaks. After checking the underside of the right wing, check the PC2 hydraulic reservoir for proper servicing. Check the aft fuselage and tail for damage and leaks. Inspect the afterburner exhaust nozzle flaps for damage and freedom of linkages, the flame holder, afterburner nozzles, and the afterburner liner for wrinkles or cracks. Continuing up the left fuselage, check the PC1 reservoir for proper servicing. In the left wheel well, check that the pressure fuel cap is secured. The fuel selector switch should be in power off, and the wing fuel manual shutoff valve should be in open. The hydraulic hand pump should be in the stowed position. Perform the same check on the strut extension and wheel as was performed on the right landing gear, and check the underside of the left wing. Check the pressure in each of the pneumatic system bottles on the gauges on the left forward fuselage. Climb up to the cockpit. Before entering, check the ejection seat. You will be checking one of two ejection seats, the Martin Baker F5 seat or the Vought low-level seat. All late model F8Us and most F8U 1 and 2 series airplanes are equipped with the Martin Baker F5 seat. On the Chance Vought low-level ejection seat, the pilot inspects the canopy actuator and then makes the following checks. Face curtain handle and canopy interrupter override handle stowed. Seat arming pins inserted in pre-ejection safety latch, and face curtain eccentric arm properly positioned, as shown by alignment of the reference marks on the arm and cover plate assembly. Seat cartridge indicator shows loaded with white line wholly visible and catapult safety pin inserted in the firing mechanism. Canopy seat interconnect cable routed and properly attached. Parachute D-ring stowed. Pull on the harness to verify that harness fittings are secured to the seat. Harness and parachute should be in good condition. Bailout bottle lanyard attached to the emergency oxygen cable clip on the bulkhead. Bailout bottle oxygen pressure up. The emergency harness release should be properly stowed. The parachute arming cable engaged and inserted through the hole at the aft end. It should be possible to feel the cable fitting sticking out beneath the handle housing. Integrated harness actuator static cable properly connected to the airplane structure. Inside the cockpit,
check that the emergency canopy jettison handle is stowed. This completes the checks on the chance vought seat. When inspecting the Martin Baker ejection seat, check the following items: face curtain handle properly stowed and safety pin in place. Canopy interrupter override handle stowed. Canopy interrupter link resting against the override lever. The drogue link line must pass through the guillotine trap and be securely fastened to the parachute withdrawal line fitting. Presence of safety wire and seal on drogue gun barrel assembly. Drogue gun ground safety pin installed and the drogue gun trip rod pinned to the bulkhead. Parachute D-ring stowed. Shoulder harness straps should be pulled to ensure proper attachment. Pull on the lap harness to ensure proper attachment. Notice that the sticker clip tabs are inserted in their clips. Check the oxygen radio disconnect lines for security of attachment. Check the bailout bottle oxygen pressure and see that its lanyard is unrestricted and attached to cockpit deck. Secondary firing handle properly stowed and safety pin in place. Emergency harness release handle properly stowed and attached to the guillotine cartridge sear. Check for the presence of safety wire and seal and ground safety pin in place through the guillotine cartridge sear. On the top of the seat, check for the presence of safety wire and seal and ground safety pin in firing sear. Curtain firing cable attached to firing sear. Canopy interrupter cable attached. Secondary firing handle cable attached properly. And the drogue scissor shackle resting on its stops. Canopy seat interconnect cable routed and properly attached. Check the canopy actuator safety pin in place. Check that the time delay mechanism trip rod on the right side is pinned to the bulkhead. Next, be sure that the emergency canopy jettison handle is properly stowed. After routing leg restraint lines and attaching garters as shown, pull the leg restraint lines to check snubber action. Very important. The blue line must restrain the right leg. The white line must restrain the left leg. The restraint lines should not be crossed or passed around the control stick. After strapping in and before flight, 3 flags are pulled to remove 6 ejection system safety pins. Safety pins are removed from the alternate firing handle, guillotine cartridge sear, face curtain, ejection gun, drogue gun, and the canopy actuator. Remember, most live heroes do not bring back badly damaged aircraft today. They return in properly inspected ejection seats. The arrangement of controls and instruments is relatively standard. Look around the cockpit and check each control for proper position. Have electrical power plugged in. Normally, you will have AC and DC power connected. However, if necessary, only the DC lead is needed for a start. Check the armament and weapon system switches off. Since the airplane has no battery, the master generator switch must be in external, and the DC power indicator must show a V in order to go through the starting procedure. Check oxygen system quantity. Fully charged, the gauge will show 5 liters. You are now ready to start the engine. Check the throttle in off and place the engine master switch on. Check the fuel control switch. It should be in normal. After exchanging ready signals with the ground crew, place the throttle in crank momentarily. At 5% RPM, move the throttle to ignite. And at 12% RPM, advance the throttle to idle. Ignition will normally take place in 3 to 5 seconds. At approximately 50% RPM, the GTC automatically shuts off the air. Electrical power is secured, and the main generator switch positioned to main. Idle RPM is 64 to 69%. The exhaust gas temperature should indicate 340 degrees centigrade or below. Oil pressure should be a minimum of 35 psi. Under normal conditions, no engine warm-up period is required. If during the start procedure a hot start occurs where the exhaust gas temperature exceeds 630 degrees centigrade, or if the engine fails to start within 20 seconds after the throttle is placed in idle, or if you get a hanging start, that is, ignition has occurred but the engine does not stabilize at idle, immediately pull the throttle to off and turn off the main generator switch. Investigate the cause of the difficulty. Check that the external starter equipment is inserted. Move the main generator switch to external and check for a V with the fuel control switch in normal and the engine master switch on. Move the throttle momentarily to crank in order to purge the engine. After 15 to 20 seconds, stop cranking. Then move the main generator switch and the engine master switch to off. If there is no damage, allow 30 seconds for fuel drainage and check to see if all fuel has drained from the afterburner section before attempting another start. After the start, with the engine stabilized at idle RPM and starting equipment disconnected, go through the system checks. We'll start with the electrical system. Recheck the DC power indicator for the letter V showing. For an AC power check, see that the attitude indicator off flag is not showing. Turn on and check all radio and navigation equipment to allow warm-up. Turn on the stabilization systems. The hydraulic system pressures should be checked by selecting utility and each PC in order and watching the system's pressure gauge for a reading of 3,000 plus or minus 200 psi. During wing spread, wing and droop actuation, and arresting hook checks, utility system pressure will momentarily drop and return to the correct pressure after the component has actuated. Similarly, actuation of flight controls causes PC system pressures to bleed off. They should return to correct operating pressure after surface deflection is completed. One note, for each 5 minutes of ground operation, the wing or droop should be cycled and flight controls moved to prevent overheating of hydraulic fluid in each system. Follow the procedure your own squadron has worked out to complete checking out the operation of the unit horizontal tail, aileron, and rudder trim systems. A check of proper control responses and the aileron rudder interconnect feature of the stab system is best accomplished by a cockpit wipeout maneuver. Basically, here's what happens. With the aileron in full throw, the rudder deflects automatically in the opposite direction. Then, by applying back pressure on the stick, the rudder returns to neutral. Violent and uncontrollable pitch oscillations in flight can be caused by improperly serviced viscous dampers. For correct operation of the viscous dampers, perform the following checks with engine running. Smartly push stick forward about 3 or 4 inches and watch for slow and smooth return to neutral. If the stick snaps back to neutral or partially snaps back, the viscous damper has been incorrectly serviced and the airplane must not be flown. The manually operated counterbalance canopy should not be open when wind force is in excess of 60 knots. The canopy is locked in the closed position by 4 rotating hook latches that can be operated from either inside or outside the cockpit. With a chance vought seat, the canopy should not be lowered with the seat and headrest in the full-out position. If difficulty is encountered in locking the canopy, retard the throttle to idle and turn off the air conditioning system momentarily. Lock the canopy and turn the system on again. now ready to taxi. To start the taxi, advance the throttle to approximately 75% RPM and release the brakes. As the airplane moves forward, retard the throttle to idle and use the nose gear steering for directional control. To obtain full steering range, taxi with the wing up. If the steering action is sluggish, depress the nose gear steering switch and cycle the rudder pedals to build up accumulator pressure. Following excessive use of brakes during taxiing or an aborted takeoff, allow a minimum of 45 to 60 minutes before attempting takeoff. An overheated tire may explode following retraction, and the resulting damage can lead to loss of the airplane. Idle RPM will provide sufficient power for taxi. Failure of the pop-open exhaust nozzles to open will result in excessive taxiing speed. A check of roll damping may be made by selecting the PC1 position and observing PC1 pressure fluctuation as the airplane rocks during taxi. To check yaw damping, observe the fluctuations on the hydraulic gauge with the selector at PC2 as you turn the airplane slightly from one side to the other. To make an engine thrust check, you must know the minimum pressure ratio for the ambient temperature as listed in the normal procedure section of the pilot's flight manual. To check the engine performance in normal fuel control, advance the throttle to military position to obtain the engine pressure ratio indicator reading. The RPM should indicate from 92 to 96%, and the exhaust temperature limit is 620 degrees centigrade. Engine oil pressure should be 45 plus or minus 8 psi. The reading of the engine pressure ratio indicator will vary with ambient conditions, but should fall within the range for the given conditions for that day. When engine performance check is complete, return the throttle to idle to make a manual fuel check. Switch to manual fuel control with the throttle in idle. Upon switchover, a decrease in RPM will usually be noted. The engine should not drop below generator cutout RPM, about 40%, and must remain alight regardless of RPM drop. Proceed to cycle the fuel control switch 3 times to bleed the fuel control of any entrapped air. With the switch in the manual position, the fuel control light is on. Advance throttle to military while observing gauges. Proper engine pressure ratio should be reached with the throttle in military. The engine will accelerate without exceeding temperature limits when the throttle is advanced with normal caution. The fuel flow indicator will show a reading of 5,525 to 7,125 pounds per hour, less 150 pounds per hour for each 1,000 feet of field elevation. Retard throttle to idle. Move fuel control switch to normal. The fuel control light will go off. This completes the manual fuel check. If the engine stabilizes at normal idle settings, perform the takeoff checklist. To complete the takeoff checklist, check the quantity of fuel in the transfer and main cells and that the fuel transfer switch is in pressure dump and the fuel pump warning light is off. Check the wings, spread and locked. Check the wing raised and the wing gear phase light off. Check that the yaw and roll stabilization switches are on and warning lights are off. Check rudder and aileron trim. Both sides of the neutral trim light will go on to indicate 0 degrees trim. Set pitch trim at 3 to 4 units nose up for normal fuel weights. Check that the speed brake switch on the throttle is forward. Override is in normal, and speed brake light is off. Check the parachute harness tight and locked. Next, check that the canopy is locked, the handle is stowed. Oxygen valve is on with oxygen light out, and the pitot heat is on as necessary. Make a quick check to see that the ejection seat safety pins and flags are removed. Flight controls are free, and the takeoff checklist is completed. You are now ready for takeoff.
Flight operations will be covered in the next film in this series. With your pre-flight checks completed, as shown in the previous film, you are ready to take the runway for takeoff. One reminder, be sure that your throttle is cradled to the cruise droop position. You will want the droop in this position immediately after the wing is lowered to the clean condition. When in position, hold the brakes and advance the throttle to military. If the engine is developing takeoff thrust as indicated by the pressure ratio gauge, engine instruments are normal, and there are no warning lights, you are ready to go as cleared by the tower. If an afterburner takeoff is made, release the brakes before igniting afterburner and let her roll. Use nose wheel steering only to line up at the start of the takeoff roll. Use brakes to maintain directional control before rudders are effective. In a crosswind takeoff, the airplane tends to roll into the downwind wing and turn into the wind. However, the ailerons become effective at low speed and can be used to oppose this rolling tendency. The rudder will be effective at about 60 knots. Lift the nose wheel off the deck at about 130 to 140 knots and sweep the airplane off at about 150 knots. Retract the gear after you are comfortably airborne. Start to lower the wing after reaching 180 knots and an altitude of 200 feet. In lowering the wing, the release switch must be held depressed as the wing incidence handle is moved to the down position. The nose must be raised slightly as the wing lowers to prevent sinking. After the wing is in position, bring the lock handle to the lock position. The wing must be down and locked at a speed of not more than 220 knots. Begin using transfer system fuel by placing the transfer switch to on. Recheck the pressurization system on. Climb to altitude using the climb schedule. For a general rule, retract the cruise droop at 250 to 300 knots prior to beginning the climb. Extend the cruise droop again as airspeed drops below 300 knots in the climb. Check the droop indicator. Also make a visual check after each actuation. If the indicator shows a barber pole, do not exceed 300 knots. For the P4A engine, observe the exhaust gas temperature limit for military power of 620 degrees centigrade below 30,000 feet and 650 degrees centigrade maximum above 30,000 feet. Oil pressure should stay between 37 and 53 psi. The ailerons, spoilers, rudder, and horizontal tail provide good control at all speeds. Maneuvering control forces are light, about 5 pounds per G. Be careful not to over-control, particularly at high airspeeds at low altitudes. The speed brake is effective and fully controllable. Extension results in a slight nose-up trim change. The fully extended brake results in slight buffeting, which increases at high airspeeds. The Crusader stalls in the conventional manner. The clean condition stall, cruise droop in, is preceded by airframe buffet beginning 30 to 40 knots above stall speed. Buffet onset may be delayed approximately 10 knots by using cruise droop. As airspeed decreases, the stall is marked by a wing drop and usually a slight yawing tendency. Recover by relaxing back pressure, adding power, and flying out. The landing condition stall is preceded by airframe buffet, which occurs about 10 to 15 knots in advance of the stall. Buffeting increases until it is moderately heavy at the stall. Slight yawing, followed by a sharp wing drop in one direction or the other, usually to the right, marks the stall.
Recover by releasing back pressure, advancing the throttle, and flying out of the stall as airspeed increases. The accelerated stall is marked by moderate buffeting, rapidly increasing to heavy buffeting. Roll oscillations, yawing, and porpoising may occur just prior to the stall. This stall is characterized by sharp wing drop and abrupt yaw in either direction. Recover by releasing the back pressure, neutralizing controls, and flying out of the stall. Do not use aileron movements in opposition to any wing drop tendency in any stall maneuver, since these only aggravate the stall and may produce a spin. Intentional spinning of the airplane is prohibited. If a spin is encountered, recovery may be effected by retarding throttle to idle and extending landing droop by the emergency system. Applying full aileron with the spin while holding full aft stick travel and deflecting full opposite rudder. Note the wing need not and should not be unlocked to blow out the landing droop. As rotation ceases, quickly neutralize ailerons and rudder and ease the stick slightly forward of neutral. Remember, if the landing droop is blown out for spin recovery, it cannot be retracted. Return to base under 300 knots, lower the gear, and raise the wing pneumatically for landing. Expect a decrease in range with the land droop out. The F8U maneuvering characteristics are normal. The rate of roll is good at all airspeeds, even at high airspeeds, due to spoiler action. In dives, caution must be exercised because of the increased altitude required for pullout. Refer to the dive recovery chart in the handbook for figures. Afterburner lights can be obtained with best reliability below 40,000 feet and above 0.8 Mach number. If the light is unsuccessful, the throttle should be returned to the military position for at least 5 seconds before the next attempt. Let's prepare the airplane for air refueling. With the wing down and the leading edge in cruise droop position, turn off all unnecessary electrical equipment to reduce electrical load and fire hazards. Place the probe switch in out. As the fairing door opens and the probe extends, the probe light will go on. A slight trim change will have to be made. The approach to the drogue is made from a position approximately 15 feet directly astern. Using the tanker and hose as reference, increase engine speed approximately 2% RPM to establish a closing speed of 2 to 3 knots. Set up so only small adjustments are necessary for alignment. Keep the closure rate constant. As engagement is made, the refueling hose will ripple slightly. Push the drogue into the refueling zone and remain in position by flying formation on the tanker. Fuel is admitted at the rate of approximately 1,340 pounds per minute. Total system refueling can be completed in 5 to 7 minutes. Once refueling is complete, reduce power slightly to back out and disconnect from the drogue. Holding the probe switch in the in position, the probe retracts, and when the door closes, the probe light will go out. The switch should be held at in for a few seconds after the light goes out to ensure that the door is fully closed. Now, before starting your descent for the approach and landing, place the defog switch to defog and regulate the cabin temperature switch as desired. From 80 to 85% RPM should be maintained during high rates of descent to prevent fogging. Enter the landing pattern according to local field rules at 250 to 300 knots with cruise droop out. Brake far enough down the runway to give yourself a good downwind leg. Extend speed brake and retard the throttle to about 80% RPM or as required to slow down. Below 220 knots, drop your gear and as you slow to 190 to 200 knots, unlock and raise the wing, holding the release switch during the movement of the incident handle. Slow to 150 knots on the downwind leg. At the 180, you should be at about 1,000 feet altitude and 150 knots airspeed. Check your gear indicators for down and locked indications. Continue downwind far enough so that you will have a comfortable straightaway. Maintain 150 knots and arrive at the 90 at about 145 knots and about 400 feet altitude. As you roll into the final, slow to 135 knots. Establish a landing attitude and slow to a minimum of 130 knots over the fence. Touchdown on main gear between 125 and 130 knots. After touchdown, retard the throttle and maintain a slight back pressure on the stick to hold the nose gear off the runway and to reduce speed by aerodynamic drag. Delay brake application until your airplane has slowed down to well below 100 knots. The rudder will be effective until you reach about 60 knots. Use the brakes for steering until the end of the roll, and then use the nose gear steering. It is important that the rudder pedals are neutralized before the nose gear steering switch is depressed. During crosswind landings, apply a combination of crabbing and side slipping in the approach. Touch down at about 135 knots and perform a transition to a three-point attitude as soon as possible. Directional control is maintained by means of the rudder. Rolling tendency is opposed by means of the ailerons. Don't establish a high sink rate. Slow speed coupled with a high sink or over-rotation may result in dragging the tail section on the landing. A wave-off is easily accomplished by advancing the throttle smoothly to military. Extra thrust is available from the afterburner for a desperation-type wave-off. Back in the line, secure the radio, IFF, TACAN, and stab systems. Then operate the engine at 75 to 80% for 30 seconds before retarding the throttle smartly to off. After moving the throttle to off, the generator will drop off the line at about 40% RPM, at which time all switches may be secured. In order to increase your proficiency in the Crusader, supplement your flight experience with further study of the pilot's flight manual. In this film, you will see the most important emergency procedures for the F8U Crusader. Included are engine failure, system failure, fire, emergency escape, ditching, forced landing, and engine outlanding. The procedures shown in this film apply to all types of F8U airplanes. First, engine failure. Indications that the engine has failed are a reduction in the engine RPM and changes in engine pressure ratio and exhaust temperature, followed by a loss of airspeed. If the engine fails before you become airborne, pull the throttle to off and apply the brakes. If necessary, use the emergency air brake. If the runway is equipped with field arresting gear, lower the arresting hook. Remember that it takes up to 8 seconds for the hook to extend fully. Normally, raising the landing gear on the deck is not desirable, but if the situation dictates, flip the emergency downlock release switch and pull up the wheels. If the engine fails just after takeoff and safe ejection altitude cannot be attained, put the throttle to off and extend the emergency power pack if time is available. Maintain minimum airspeed for adequate control response and land straight ahead. The canopy should be jettisoned if you are going to run off the runway. If engine failure occurs during flight, immediately pull the throttle to off. If the fuel transfer switch is not in on, switch to that position. Do this before engine speed decays if possible. Extend the emergency power package. After a slight delay, switch the emergency generator to on. Check for indications of adequate emergency hydraulic pressure and electrical power. If everything looks normal, attempt an air start. First, dump the cabin pressure and make sure the defogger is off. Turn the UHF off above 27,500 feet if a start is not obtained in 3 minutes. Fuel control can be in either normal or manual. The best conditions for an air start are altitude under 35,000 feet, airspeed 170 to 250 knots, and 17 to 30% RPM. But don't wait to reach these values. Attempt the air start as soon as possible. Put the throttle in ignite, then in idle. Watch the tachometer for indication of the start. If the engine fails to start, wait 40 seconds before trying again. For the second try, have the fuel switch in manual, in case the flameout was due to failure of the fuel control. If the second try fails, and time permits, wait another 40 seconds. This delay is necessary to permit the ignition timer to complete the previous cycle. Then depress the ignite switch manually and try again. When the start is obtained, allow the engine to stabilize. In manual fuel, the throttle position and EGT are critical and may have to be monitored closely. Fuel flow should be at least 750 pounds per hour for successful relight. Check the instruments. Restore master generator operation. Reset the roll and yaw stabilization switches. Turn back on the equipment you have turned off. For an air start above 35,000 feet, coming back immediately to throttle off, hitting the igniter and returning to idle may relight the engine before RPM has dropped too far. The system's film covers the procedures for most system failures. We will go over a few special points. If the afterburner fails to cut out when the throttle is moved inboard, the throttle should be pulled back past the afterburner detent. When the afterburner goes out, the throttle may again be advanced to a position just below the afterburner detent, allowing engine operation up to approximately 85% RPM in military power. Do not relight the afterburner unless necessary. If a failure occurs in the utility hydraulic system, you will still be able to get into the landing configuration. Approaching for landing, wait until you are slowed to no more than 220 knots. Use the emergency procedures for lowering the wheels, extending the leading edge, and raising the wing. These emergency procedures make use of air from the pneumatic system. No further change in configuration is now possible until the utility system has been reserviced. In the landing condition, and under 180 knots, the Crusader can be controlled safely without yaw or roll stabilization or trim control. However, in case of failure of pitch trim, the T-handle must be pulled out and used to control the pitch trim manually. In case of a main generator failure, when you go to emergency generator operation, remember that extending the power package reduces your range by about 18%. Descend to an altitude below 30,000 feet. This lessens the possibility of a flameout due to loss of fuel boost pressure. Since only one fuel boost pump is operating now, do not use afterburner unless absolutely necessary. Observe the nose-down restriction in order to avoid uncovering the engine fuel outlet in the main cell. These restrictions are as follows. Above 1,200 pounds fuel remaining, do not exceed 20 degrees nose down. Between 600 and 1,200 pounds, do not exceed 10 degrees nose down. And under 600 pounds, maintain level or nose-up flight. Smoke or noxious fumes in the cockpit can be caused by an electrical fire, air conditioning turbine failure, or from engine oil. If an electrical fire is indicated, attempt to isolate it by switching off the related system or systems. The smoke can be cleared by dumping the cabin pressure, turning off the defogger, and turning the emergency vent air knob to open the air inlet. Now let's take a look at a different situation. If the fire warning light comes on, pull the throttle back to idle. If the light goes off, the probable trouble was engine overheating. Resume normal operations, taking care to avoid further overheating. If the fire warning light goes off and comes back on, or stays on, check the EGT and RPM for erratic indications. Check for smoke behind through your mirror or have your wingman check. If at least 2 indications of a fire still exist, shut down the engine and attempt an air start, or abandon the airplane. The emergency escape procedure for abandoning the Crusader depends on whether you are using the Vought low-level seat or the Martin Baker seat. In either case, reduce speed to under 400 knots by extending speed brakes, retarding throttle, or pulling up. In the Vought seat, at altitudes above 500 feet, sit erect with head against the headrest, legs extended, and feet resting on the rudder pedals. Grasp the face curtain in this manner and pull in one continuous movement. The canopy jettisons and the harness locks. Then the seat will eject. If the canopy does not jettison, pull the canopy interrupter override handle, then pull the face curtain again. The seat will eject through the canopy. The Vought seat can also be used for low-level ejections down to about 150 feet in level or climbing flight. For low-level ejection, place the wing downlock handle in unlock. This causes a snubbing cable attached to the seat to be pinned to the deck. Then go through the same ejection procedure. The action of the snubbing cable serves to separate the pilot from the seat. Pilot separation then arms the parachute opener. In the Martin Baker seat, you can safely eject as low as 50 feet and 120 knots, if in level or climbing flight. Descending attitudes require higher altitudes for safe ejection. Head back, legs extended, pull out and down. Here are the alternate firing methods for the Martin Baker seat. If you cannot reach the face curtain handle, use the alternate firing handle. A sharp pull is required. If all methods for ejecting the canopy have failed, pull the override handle to permit ejection through the canopy. Ditching the Crusader is not recommended. If ditching becomes necessary, leave the wing where it is. If the wing is down, establish landing droop pneumatically. Lock your shoulder harness. Jettison the canopy. Cut the engine. Establish a glide at about 170 knots. Try to touch down at 145 knots in a nose-high attitude. Immediately after forward motion stops, pull the emergency harness release handle and abandon the airplane. In the event of a forced landing with power, dump fuel if time permits. A slight nose-up attitude gives maximum dumping. Before landing, place the dump switch to off, even if you're not through dumping, since electrical power to close the valve may not be available after landing. Use the normal approach and landing techniques. In the Crusader, an engine-out landing requires precise judgment and allows little margin for error. Never attempt a flame-out landing in an F8U unless you are thoroughly qualified in the airplane and have currently exhibited a high degree of competence. Normally, you should eject or bail out. If no other alternative is available, a flame-out landing may be attempted. The landing should be made on a runway equipped with arresting equipment or at least 10,000 feet in length. Enter the pattern lined up slightly to the right of the runway, gliding at 220 knots airspeed. Speeds given here are for gross weights up to 23,000 pounds. The cruise droop and emergency power package are extended. Throttle and engine master switch are off. Roll and yaw stabilization are off. Approaching the high key, extend the gear and raise the wing. Windmilling of the engine should provide enough hydraulic pressure to operate all utility system components. The exact time of raising the wing and the use of the speed brake can be controlled to bring you to the exact high key position. Slow to 175 knots. Trim 3 to 5 degrees nose up. Complete all radio transmissions. Turn the emergency generator off. This is critical. You must turn the emergency generator off to avoid possible loss of control power prior to touchdown. At the high key, slightly to the right and just short or alongside the touchdown point, you should be at an altitude of 8,000 feet. Roll into a relatively steep bank to prevent traveling too far upwind. Excess altitude may be dived off during the turn. Do not attempt to lose altitude by delaying this turn. This is the standard 360-degree pattern. The low-key position is the critical point in the approach. Altitude should be 4,000 feet. Minimum altitude is 3,000 feet. The position is 5,000 feet downwind of touchdown point. Excess altitude at low key may be lost by delaying the turn slightly or by dissipating the excess in the turn to final. At the 90, altitude 2,000 feet, speed 170 knots. Recheck emergency generator off. Rolling out on final, altitude 1,000 feet, speed still 170 knots. Maintain a stabilized airspeed of 170 knots. As you near the ground, start a gradual flare. Hold the airplane off until airspeed is down to 140 knots. Then touch down before airspeed bleed-off causes loss of control. The landing once again in slow motion. Because of the pattern precision required, pilots inexperienced in the F8U should abandon the airplane rather than attempt an engine-out landing. In this film, you have seen some of the emergency procedures common to all types of the F8U Crusader. Supplement this information by studying your pilot's handbook. Earlier films in this series show the systems and operating procedures for the F8U-1 and the emergency procedures for all types of F8U airplanes. This film shows how the F8U-1E and the F8U-2 differ from the F8U-1. Both of these airplanes have an improved intercept capability due to the installation of the APS 67 radar. In this film, you will see the intercept and attack procedures using this radar. First, let's take a look at the airplane. This is the F8U-1E. In external appearance, it looks just like an F8U-1. The F8U-2 is an improved version of the 1E with a more powerful engine, the J57P16. The large capacity pneumatic system air bottle has been increased to 1,100 cubic inches, and all three pneumatic system pressure gauges are located on the right-hand forward fuselage. A pair of air scoops have been added to supply additional cooling air to the afterburner. Ventral fins, one on each side, have been added to improve directional stability at high Mach numbers. The overboard fuel vent is now part of this fin. The cockpit arrangement in the F8U-2 and the 1E differs from the cockpit in the F8U-1. For example, the scope for the APS-67 radar has been added. The control panel for this radar is on the left console. The instrument panel arrangement is somewhat changed. The armament panel has also been changed and relocated. It now contains the TACAN DME indicator. 3 hydraulic pressure gauges are used, replacing the single gauge and selector switch. Due to the addition of radar equipment and the resultant increased electrical requirements, a 12 kVA AC generator and a 68 ampere 28 volt DC generator are installed in both models. The air conditioning panel has an auto manual selector switch incorporated to control inlet temperature automatically or manually. In manual, the pilot can regulate the temperature control bypass valve directly. However, it will now be necessary to adjust the controller knob to make temperature corrections for each change in flight conditions. The emergency canopy jettison handle is now a grip-type handle located on the instrument panel hood. Operating procedures for the F8U-2 and for the F8U-1E are generally the same as for the F8U-1. However, the F8U-2, due to its larger engine, has a few important differences. The J57P16 engine in the F8U-2 idles at 65 to 68% RPM. The RPM for takeoff in the 2 is higher than in the 1, between 97 and 100%. Maximum permissible engine speed on takeoff is 103.3%. Now let's see how to run an intercept mission in the F8U-1E or F8U-2 using the APS-67 radar and Sidewinder missiles. Put the radar function switch in standby and allow a warm-up period of 3 to 5 minutes. Then switch to the search mode. Turn the radar gain all the way down. On this radar, adjust the brilliance control before adjusting the gain control. Turn the brilliance up until the artificial horizon can be clearly seen. Now turn the gain up as necessary and adjust the focus. The FTC switch provides for reducing scope clutter in the search mode. Leave it in normal, except when needed. Set the tune knob to auto to obtain automatic radar receiver tuning. The test button provides the pilot with a means of checking radar performance. Holding the test button depressed displays a series of false targets covering at least half of the scope. A fewer number of test targets or less coverage may be an indication of poor radar performance. The radar lock-on sensitivity can be checked by locking on the most distant target possible. To lock on, rotate the minimum range strobe out to just below the desired target. Then turn the radar function switch to the range position and continue to hold the test button depressed. A change to the lock-on display indicates that the system is operating properly. Now set up the armament panel. Turn on the master armament switch. Select the desired missile and turn up the missile volume control. Vectors from GCI direct you to the vicinity of the target. Operate the radar in the search mode. This mode provides a roll-stabilized radar sweep 45 degrees on each side of the airplane heading, and a total of 14 degrees in elevation centered about the armament datum line. No pitch stabilization is provided. If target altitude is known, maneuver to an altitude 2,000 feet below the target. This is the optimum vertical separation for detection in straight and level flight. If you do not see the target on the scope when GCI says that it is within radar range, step the nose position of the airplane up and down until the target appears on the scope. When the target appears on the scope, maneuver to position it dead ahead. The artificial horizon permits you to concentrate on the scope during the intercept and still maintain your attitude orientation. When the target range closes to 8 miles, adjust the minimum range control until the range strobe is just under the target. Then shift to the range mode. The scope shows acquisition, then lock on. The target light on the missile release computer goes out. You are now in the attack phase. The antenna has locked straight ahead to the armament datum line, and the radar has shifted to a conical scan. Maneuver to center the steering dot. When the steering dot is centered, the target should be visible in your fixed gun sight. When the antenna is pointing straight at the target, the size of the circle indicates the range to the target. If you allow the target to drift out of the antenna scan, the radar presents a warning display, then reverts to the acquisition phase. The lock-on procedure must be repeated by going back to search, adjusting the range strobe again, and repeating the lock-on. Now maneuver to keep the steering dot centered. When the missile locks onto the target, the missile tone changes. When the target range needle lines up with the Sidewinder maximum range needle, and the target and G-limit lights are out, you are within the missile envelope. If the G-limit light is not on, fire. The missile finds its target. In this film, you have seen how to fly an intercept mission in the F8U-1E and the F8U-2 using the AT-67 radar with Sidewinder missiles. Know these procedures well to take full advantage of this radar, and it will improve your chance of succeeding on every intercept mission. This is the F8U-1P, the photographic version of the F8U Crusader. Its photographic system is capable of handling general reconnaissance, mapping, beach, and night reconnaissance photo missions. In this film, you will see how the F8U-1P differs from the basic F8U-1 and how to operate the photo system. First, let's take a look at the airplane itself. The 1P can be identified externally by the forward camera station blister, camera station windows, and generally square lower forward fuselage. This airplane carries no armament. In place of the rocket pack, it carries an extra fuel tank, the forward main cell. This cell has its own booster pump, and with the main cell supplies fuel directly to the engine. The electrical system consists of a 12 kVA 115 and 200 volt AC generator and 68 ampere 28 volt DC generator. AC power to the photo system comes from the secondary AC bus. DC power is obtained from a transformer rectifier in the photoelectrical system. The pneumatic system is supplied by a single 900 cubic inch air bottle instead of the 3 bottles used in the F8U-1. For this reason, the 1P has only one pneumatic pressure gauge, which is located on the right forward fuselage. Before you start on a photo mission, the photographer's mates must prepare the cameras and make settings on the camera control equipment. Settings are made on the station computer in the equipment bay in the forward fuselage. And the RDA servo power unit settings are checked. You will notice several changes in the 1P cockpit. For example, the camera viewfinder replaces the radar scope. A radar altimeter and a free air temperature gauge have been added. The fuel transfer switch is in a new position. While you're making your pre-flight cockpit checks, check the master camera panel to make sure that the camera power switch is off. Set in the speed and altitude you will be using during the photo run as a backup for scanner operation. The camera station control panel contains separate operating controls for each of the 4 camera stations. Station 1 is the nose camera, which can be mounted at 10 or 25 degrees depression angle. Station 2 can be used for a single vertical camera, individual 30-degree obliques, or a trimetragon arrangement which provides horizon-to-horizon coverage. Depending on the type of cameras installed, Stations 3 and 4 can be used for photographing vertically at various oblique angles or for night photography. The depression angle for these two stations can be varied from the cockpit. The film counters should show the amount of film in the cameras installed for this flight. Before arriving at the target, set the view selector to wide angle. Turn on master camera power and check scanner operation. Camera operation can be selected for stick control to use the trigger switch or for automatic operation in master using the operate switch. Make sure the ready light comes on for each station to be used. Check the station controls for the desired depression angle. Always be sure the camera is not operating before rotating the mount to avoid damaging the shutter mechanism. Adjust the viewfinder drift setting if desired. Turn on the grid illumination. The exposure meter indicates the relation between light reflected from the terrain and the camera diaphragm openings or slit width. Set the exposure control to adjust camera diaphragm openings or slit width. A meter reading of normal indicates that the cameras are properly adjusted for the amount of light being reflected from the terrain. The F8U-1P carries a tape recorder to permit you to record your comments during the photo run. To use it, turn the lever to on and allow time for the recorder to warm up. Then turn the recorder switch to on. When over the target, start the cameras. If the grid lines do not track at the same speed as the ground image, the scanner is not operating properly. Turn the operate switch off. Switch to computer operation and adjust the computer manual inputs until proper movement of the grid lines is obtained. Then turn the operate switch back on. At the end of the run, it is important that you turn off the camera operate switch first. With pulse-type cameras, extra pictures can still be taken if desired by using the extra picture switch. In shutting down the camera system, the order of the steps is important. With the camera operate switch off, check that the mount is in vertical. Turn the station control switch off, and then turn the camera power switch off. For a night photo mission, only camera stations 3 and 4 can be used, since these are the only stations large enough to accommodate the cameras used for night missions. The light monitor detector is removed. This is the unit that measures the amount of light reflected from the terrain for determining exposures during a day photo mission. In its place is put a flash detector. On the night photo mission, this unit will generate a pulse to trigger the cameras each time a flare ignites. The flare ejectors are not loaded until the circuits have been checked for stray voltage so that the flares can be loaded safely. Make sure that camera power is off. On the flare release panel, check the flare arming circuits by turning on the flare arming switch. If the ready light does not come on, the circuits are not energized. Turn the arming switch back to off. The flare ejectors can now be safely loaded. Camera operating procedures are similar to those for the day mission. However, the system must be operated in the computer mode. About 10 minutes before arrival over the target, turn the camera power switch to on and the station control switch to on. Place the flare ready switch in ready. Select the firing order. When train is used, the left flares eject in sequence, then the right flares eject. When you start camera operation with the operate switch, a flare ejects. It ignites after a preset delay. The exposure is made, and the shutter closes. The camera recycles and is ready for the next picture. The failure light indicates that all flares have been expended from the position selected. When the mission is completed, if you have any flares left, eject them with the salvo switch. And secure the photo system in the reverse order that it was placed in operation. To prevent cockpit and camera compartment fogging during a rapid descent, turn on the defogger and allow about 5 minutes for warm air to circulate. In the descent, maintain at least 85% RPM. The versatile photographic system of the F8U 1P is capable of taking pictures at the maximum altitudes and speeds of the airplane. To obtain the fullest use of this system and for your own safety, supplement the procedures you have seen here by studying the pilot's flight manual.